Good morning. Happy Friday. We are just about to get into it. Excuse me. Day 16. These are getting harder. Getting fun. Getting exciting. Let's have a little looky-loo here at problem 16. And hope we know how to solve this type of problem. We'll see. I don't even know what it is yet. The sensors have led you to the origin of the distress signal. Yet another handheld device. Just like the ones the elves gave you. However, you don't see any elves around. Instead, the device is surrounded by elephants. They must have gotten lost in these cells, and one of the elements apparently figured out how to turn on the distress signal. That's hilarious. The ground rumbles again. Much stronger this time. What kind of cave is this exactly? Scan the cave with your handheld device. It reports mostly igneous rock, some ash, pockets of pressurized gas, magma. This isn't just a cave, it's a volcano. I thought that might be the case because after you solved yesterday's puzzle, you could see this volcano. So I was thinking the next puzzle was going to be about a volcano. You need to get the elephants out of here, quickly. Your device estimates that you have 30 minutes before the volcano erupts, so you don't have time to go back out the way you came in. You scan the cave for other options and discover a network of pipes and pressure release valves. You aren't sure how such a system got into a volcano, but you don't have time to complain. Your device produces a report of each valve's flow rate if it were opened in pressure per minute, and the tunnels you could use to move between them. Move between the valves. The tunnels you could use to move between the valves. Okay. There's even a valve in the room you and the elephants are currently standing in, labeled A. You estimate it will take you 1 minute to open a single valve and 1 minute to follow any tunnel from one valve to another. What is the most pressure you could release? So we have room labels, flow rates, and passages. So this is a graph problem. The question is, are these edges? The edges takes 1 minute to travel between them, but these change the pressure. What is the most pressure you could release? Let's see here. All of the valves begin closed. You start at valve A, but it must be damaged or jammed or something. Its flow rate is 0. So there's no point in opening it. However, you could spend 1 minute moving to valve BB and another minute opening it. So 1 minute to move, 1 minute to open. So our edge weights are 1 for moving. Interesting. And then you spend a moment there. I'm wondering if the whole thing is encoded as a graph and then you do a search. Do a search of the graph to find it. I don't know if that would get too big because, well, let's keep reading. Total pressure released. So the pressure released at that moment would be for the rest of the time. So it's 13 per minute. There's 28 minutes remaining, so 364. You spend your third minute moving to valve CC and your fourth minute opening it, providing an additional 26 minutes of eventual pressure release at a flow rate of 2 or 52 total pressure released by valve CC. Yeah. Okay. Making your way through the tunnels like this, you could open many or all of the valves by the time 30 minutes have elapsed. However, you need to release as much pressure as possible, so you'll need a methodical approach. I think I understand the problem. Valve D, say 1-2 minutes, third minute we open it. Oh no, 1 minute to move, 1 minute to open. Third minute it starts releasing, so we don't start releasing pressure till the after it's open. That makes sense. So 20, we move, we open, that gets added, so we have a counter here. So we kind of have, let me think about this. If we were to turn this light on here. So we have a graph, and then at each, so we have a map of navigation to each one. This feels like like we need to know the shortest path between each node, and then moving to that node at this time step would increase our pressure by some amount. So we want to know at each location, how long is it going to take to get to all other locations? And then if we were to move to that location, how much pressure could we reduce at that location? So we have like, it's going to be 3-dimensional graph, because the graph, so you can sort of think of a graph that sort of has the entire layout, and then if you choose to open a valve, it sort of like goes down a level to a whole graph where it's the same graph as above, but now moving back to this edge would increase your sum by 0. So it's like, could do some kind of memoization to recursively solve it. Or we could do, I think if I have edges, so I think, yeah. So first, let me get this thing parsed in. Let me parse this into a graph and then think about it. But I'm pretty sure I'm gonna need an all pair shortest path. So I'm gonna need the shortest path. I don't think I want Dijkstra, because I need to know the distance between each path, and then I need to search, find. I'm worried it's gonna get too big. How big is my input here? Let's see. Not insane. So we'll have a, like, what is this? How many lines is this? Input 58. The ones that are zeros, I don't think we care about, except that they're could be part of a path. So we don't care about. Okay, so it's not as bad as I thought. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Looks like we have 14. So like 56 by 56 by 14. That's doable. That's doable. What's that? What was that? 58. Yeah, 58 times 58 times 15. That's not bad. And maybe I have an off by 1 or 2. Yeah, this is our search space. Not bad. So I can build up this. I can build up this graph, and do. And then you just search and find the. Yeah, I'm pretty sure this is our search space. We have 57,000 combinations, and then you just. So you build it up. And then you find the one with the largest number. Okay. Yeah, so there's 58. the possible combinations, I think. All right, I could be wrong. I might have done that math wrong. We're gonna find out. Let's we're gonna build up a cave system here. It's gonna be our graph. Public record cave. And our cave is gonna have rooms. I'm gonna give them labels, just A's. I need to look up tables here. So every tunnel has a flow rate and edges. So we'll have a dictionary. Public dictionary. String to flow rate. Flow rates. And then we have string to list of string edges. All right, so we're gonna, that's the thing that we're gonna pull in here. So every node has a flow rate, and then every node has a path it can reach the other nodes from. Okay, so let's parse that in. Take it here. Build up a parse method. Public static cave parse. String row. So we'll parse in a single row. They look like this. So row dot replace valve base with nothing. String tokens. Eventually, we're going to turn this to a... We're going to split this eventually. We're going to replace as flow... No. Yeah. As flow rate equal with a space. And we're going to replace... comma, tunnels. I want to leave that semicolon in there, actually. I'm going to leave the semicolon in so I can split the left and right side. Comma, so I'll leave it in. Tunnels lead to valves. And then we're going to have the lists there. This should get replaced with empty string. And then we split on semicolon. And we'll say that yeah, because we have a list at the end. So the left half string tokens dot split. Well, let's split this on that semicolon space first, and then we'll say that string array flow. The first part of this is going to be token or node flow is tokens of 0 that replace that. Split on a space. And then our edges is going to be equal to our tokens at index 1. We already split it on that. I'm going to remove tunnels to valves and then split on comma. Okay. And then we'll turn that to a list. Like that. That becomes our edges. This is going to need to take in a cave to build. And then we will say to build dot flow rates node flow. The left side should be the edge, the node name. Flow rates of this is equal to int.parse node flow of 1 to build dot edges dot not add node flow 0 equals edges. Okay, this should build up my this builds up this reads a single row. I'm gonna call this add node, and then we have parse node. Let's make it non-static because we're doing it on a cave, and we can get rid of these two builds. Okay, so we parse in this public static cave parse string array rows. So now we're going to parse in the whole input. Let's think here. We construct a cave first. Cave C equals new cave. Tell me I don't need to have that there. And we're going to return this at the end. Let's rename that cave. And then for each row, we are going to parse a node in. Okay. Then I guess it would be nice to have a toString just for sanity checks. Public override toString. We will do the following. We will say let's do a string builder. String builder, string builder. Import this. For each, it's going to be builder dot append cave. And then we want to loop through for each when string node in flow rates dot keys. We are going to do builder dot append do 2 spaces. We'll do the name of the node. We'll do the flow rate. And then we'll have the list of edges. Like this, and we'll do edges of this node, and then we gotta join them. String dot join commas. All right, let's do a sanity check here. Oh, we gotta add a new line here, and then a new line. Then at the very, very end, builder dot append close curly brace. That's it. Oh, it wants me to do a char. That's funny. And then we'll return builder dot toString. Okay. Let us do a sanity check here. Can we parse in our cave with our sample input just to make sure we're not crazy? Program cave equals cave dot parse. Oh, we gotta make an example file, new file, example. Parse rows, and then we're gonna load that in. String array rows equals file dot read all lines, example.txt, and then let's console dot write line our cave. Let's see what our cave does here. .NET run project solution. All right, let's see here. This is wrong. Tunnel leads. What's going on with that? H. Oh, if we go to a sync. Okay. There's a grammatically correct input. Okay. So we can, that's easy. That's an easy fix. In our cave, we could possibly have tunnel lead to valve. There we go. DIB CCAA B C A E F D E G F H G A J and I 013 220 322 21. Okay, I have my graph parsed in, so my graph parser is fine. I need to do the distance between each one, so I got to do a all pairs. So it's not finding the shortest path from the start node to an end node, so it's not just Dijkstra's. I actually have to do a all pairs shortest path. All pairs shortest path. I forget what the like fancy name. It's like, I want to say Kruskal's, but Kruskal's and Prims are also shortest, like single pair shortest path. But essentially you got to calculate all pair shortest path. So I think it's like, anyway, it's okay. But we want to do dictionary from string to string. So node to node to int. So we're going to calculate shortest path. Shortest, not the actual shortest path, it's the like travel time. Yeah. So This is the travel time from start to end. So start, end. So between any two nodes, how long does it take to get between them? So that's going to allow me to construct a search of the graph more easily. I guess I don't have to do that, but it's going to make my search space smaller by doing it. Okay, so public really public dictionary string start string and int. I want to have a function that can construct this, and I just save it. Build all pairs shortest path. And to do this, so travel, we're gonna start out with this being not initialized. All right, so here's what I'm gonna do. I'm gonna be a little clever about this, and I'm gonna call this one's gonna be something that starts out null. And then we will have a public getter, public dictionary string start string end. Which it doesn't matter. It doesn't matter. I don't need to be clever. I don't need to. I'm the only one using this. I don't need to do anything special. All right. Basically what I'm going to do is I'm going to say if travel time dot count greater than 0, return travel time. Otherwise we construct. I just didn't want to I didn't want to be constructing it multiple times. And this is actually going to just build this thing up, so I can just do this. Build shortest paths. All right, so this is going to be a triply nested loop that goes all of our keys. So string, what is our flow rates dot keys? What does this give me back? What is this? Gets a collection in the dictionary. Yeah, but what's the type? Var keys. Is this a string something? What is it? Can I implicitly convert? It's a key collection here. I'm just gonna do to array. All right, so we're gonna do for string tough names here. Oh, we have to initialize it first. So we want to set, okay. So we have to do travel time for each string k in keys. We got to initialize values in this actually. So we're going to start out saying that travel time from is 0. You can get to yourself for the cost of 0. And then we're going to do all of our neighbors first. So we're going to initialize it, set for every key, and then for each, what would that be? Yeah, for each string, we'll call this node. We'll change key to node. Neighbor. I'll call this nodes. This isn't neighbor, this is node. For each string neighbor, in edges node, travel time node neighbor equals 1. So all of our neighbors have a distance of 1. And then I need to like iterate a bunch of times updating it. So it's like a triply nested loop. It's one of the few times I will let my students do a triply nested loop. So I always forget. I'm always so it's sort of like start in nodes. So the idea for each start string end in nodes. So the idea here is all pair shortest path. And then this is just like for each string best so far in nodes. That's sort of what that one represents, I think. Let's think about this real quick. So we're gonna say travel time from our start to our end is equal to the minimum of the current travel time from our start to our end. So we'll do this. Int current speed equals travel time, start to end. This is sort of like the fastest we've found so far. So if that's the fastest we've found, alternate path. Otherwise, update it for the alternate path. Is this right? Let me think here. I think this is wrong. I think I need to do start here. And then the alternate path is going to be travel time from every other node. Travel time from our start. Hang on. I almost got it. I'm trying to do this without looking it up. I think I'm gonna get it. All right, let me go to this, to the bad naming version. Because my brain can, it's like, this is what they always do in textbooks, and I hate it because it's hard. Like but my brain can remember it. I was so this is, okay. So my current speed happens to be the best so far to where I'm trying to go. All right, so this is start. This is best. This is best so far, or like start. This is where I'm trying to start from. So this is start. This is where I'm trying to go to, I think. And my alternate speed happens to be, what if instead I went from start to K and then from K to J. Yeah. So this is my start, this is my destination, and this is my alternate route. I'll just call alt. Yeah. So my start to my destination. So I'm going to find the shortest path to this node. And then I update it to be the min like this. And is this right? I'm missing. Oh, my graph's gonna. It's gonna yell at. This is gonna die. If I try and get the current travel time and it doesn't exist, so I need to sort of initialize all the other ones to like infinity. Just one little step I'm missing here. For each node and nodes, for each node in nodes. So we actually got to initialize this first for each other in nodes. If node equals other, we do this. Well, let's do this. So do travel time of node other is equal to, and we'll do a can we do a switch? Can we do a switch here? Can't quite do a switch. I want to. Else if the node is in our neighbor list, if edges of this node dot contains other, our travel time's 1. Else travel time from node to other is equal to essentially infinity. But if I did math, there's not like an infinity for integers. But what would be the max distance here? I could just do something sufficiently large. So we'll go with 1,000,000. That's essentially infinity. All right, so that'll keep my program from crashing. Okay, what are we doing here? Let's try this. Let's look at what our graph says and see if we can reason about it and see if it makes sense here. I think this is how ij, so the distance from I to j, from my start to my destination, is either the current speed, or if I find a better speed, is this right? The order of these is important. Because I feel like this is the outside one. Let's see if this makes sense. I don't want to look it up just yet. I always like to challenge my brain to keep it together. Let's do a public I want a nice way to print this. It'd be nice because it's basically a matrix that'll be relatively big. For this one, it won't be. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it'd be 10 by 10. So it'd be a 10 by 10 matrix. Be nice to have a little way to print that out because there's going to be 100 things in it. Void print adjacency, print matrix, print travel times. All right, let's see if we can do this. It's going to be for each. So string nodes is going to be flow rates.keys dot to array. Let's print that out. So we'll do a console dot write line string dot join, put vertical bars between it on nodes, and we need to have a little bit of padding at the beginning. Each one's going to be 2 characters wide, so I'll put 1, 2, 3. So we have the label for the other one will be 1, 2. We'll have a space, a vertical bar, and a space. Yeah. Plus, at the very end, we'll put a plus and a vertical bar. Let's see here. Program. Don't need to do that. Cave.build shortest path, and then cave.print travel times. Let's try that. Okay, and then I gotta go the other side, but that's gonna be for each row. Okay, I can close those two for now. Let's close that. And then we're gonna do for each string node from in nodes. We're gonna start the line with console.write from space vertical bar space, and then the adjacency, our dictionary here. Yeah. For each string 2 in nodes. That will be an issue, but we'll deal with that when we get there. Int time is equal to our travel time from to, and then we'll do time. Let's create a constant here. Public const int public const int equals 1,000,000. Not really infinity, but just in case I need to change it, we'll say time is inf. Do string val time. If time is infinity, we will do star. Otherwise, we will format our time to have 2 characters. Then console.write our time and a vertical bar and a space. Yes, I could do it so that it prints itself like this. There we go. And then console.write line. Put the last vertical bar in. All right, let's try that. And does this? Oh, that's interesting. Oh, because I'm doing time, whereas I want it to be val. Okay, does this make sense in our graph? Go from A to B should be 1. So clearly this is incorrect. Clearly this is incorrect. And from B to A should be 1. Interestingly enough, I could actually do this and just compute 1/2 of the matrix. That's an interesting thought. I didn't. It's flipped, so or mirrored along this axis. So I actually don't need to compute these if I need to, but I don't think that's gonna be a time issue there. Okay, let us keep looking here. I'm not initially. If node that contains this isn't working. The 0 worked. For some reason, I'm not setting. My edges of A should contain BB. Maybe I'm not trimming. I'm not trimming properly. That's what's going on. In my parse. Ooh, comma space. Will that do it? I keep opening a new terminal, my hotkey. .NET run project solution. There we go. That looks better. Okay. So I think I have my all pairs shortest path working. At least this isn't dying. D only takes 1. C to get to G. Let's see if that's right. A, G, what are the paths to G? G only appears on F. All right, I'm just gonna look it up, make sure my all pairs shortest path is working. I'm gonna make sure I haven't done it wrong. All pairs shortest path. Floyd Warshall. Okay. Okay, so I do have these mixed up a little bit. I had a feeling that my triply nested loop wasn't quite right. So let's think about this. They're doing I to J. So this should be start. And this is my destination. And then this one is my alt. So I update my I to J. That makes sense because I need to update my start to destination I times. So I have to do it once for each possible pair. I to alt and alt to dest. Okay. All right. I had it slightly wrong. I knew I needed 3. I couldn't remember my start, destination, and alt. Okay. There we go. I hope. Otherwise, I'm gonna be real sad. Let's test it on our full input just to make sure it doesn't crash. This will be much wider. Yeah, let's output that. APP. Just to give ourselves, it doesn't crash, but we can get a little confidence here. Okay. All right, so we have that. All right. Let us keep looking. Okay, so I have my graph. So now the idea is I need to do some kind of search where I'm starting at, I start at position AA. That's a given, right? Yeah, you start in AA, and each room, if you turn a valve on, it takes a minute. So we have like an amount of time. Let me create a new file here, solver, explorer. I like to call it explorer. All right, so public class explorer, public record explorer, cave C. Okay, this is the cave they're exploring. I need to take a quick, I gotta deal with, all right, I will be back very, very soon. I promise I'll be back in just a moment. But enjoy the sweet sound while I'm filling up my coffee. Thank you for your patience. Let us continue here. So I have my graph. I know that from any room, I know how long it takes to get to another room. I need to construct sort of a benefit at each time step, right? So I have like this third dimension of time, and how much benefit do I get at each time step if I turn a valve on in a room that was not already on? So I have this function of public int benefit int time remaining string valve or like room. Okay. So this assumes that room is currently not on. So I'm gonna have to track. So there's like this state of which rooms are currently turned on that I have to keep track of. So the benefit is time remaining times flow rates of room if it has not been turned on. This is where it's tricky. So like we need a third thing here that is like a bool array of whether or not the valve has been turned on or not. I'm gonna do a tricky thing here. This is really, I want a, you know, oh, this is annoying. I need to be able to say public dictionary string to bool is on. Hash set. Here we go. Hash set of is on. Okay, so we're gonna do hash set. This will take in a hash set. So we need a set of strings is on. So I could do, so I've coded myself slightly into a hole here. Is on. So if, all right, so we have sort of this benefit. We're gonna say is on dot contains room. If it's already on, we get no benefit for visiting that room. If it's not on, we get the time remaining times the flow rate of the room. So I need to sort of memoize this somehow in my exploration. This is, so I want to be able to take my, I could do this. Yeah, I could do this using a single integer and doing like some bit masking. If I could translate each string to a position in that integer, and then you could do some interesting bit shifting stuff. I'm worried. Can I make a, want to memoize this. But I don't think I can use this as a key. I can't, okay, all right. So I'm gonna do public int string, public int to int, and I need to do it based on a node. And I can calculate this order once, hopefully. So the idea here is I'm going to take my flow rates dot keys dot order by I just want to do a regular string compare. Order by K dot. So the sort doesn't really matter. It's just this is going to give me the indices that they were added. Oh, I can do this here. Public dictionary string to int IDs identifier. I should really basically. I hate how many dictionaries I have here. I should have an object. So this is string to this, string to this. This one here is okay, and then I have a string to this. This should all be one object, or like one record. This should be a record. So this is just like telling me I need to have a new thing called location. Public record location. And my location should have a flow rate, a list of edges, and an identifier. So it should have an int ID, int flow rate, and a list of string edges. That's what this is telling me, and then I should have a dictionary from string to location nodes. All right, let's refactor here because this is getting hard for my brain to process. Yeah. I can still do that then. All right, because my key is still this. I can still have a memoized dictionary thing. Okay. Next, when we parse now, we're gonna create a node. Public. We'll just do an int ID here. Int ID. Int ID equals 0. ID plus plus. And we will create a node. Node n equals new. Not nodes, node. Location. Node is equal to new ID int dot parse node flow 1 and edges. And we say that nodes of node flow 0 equal to node. All right, and then we need to get rid of all of these. So this now becomes for each node these are like our node, like the key for our nodes now. So now this would be node at node, nodes at node, edges, node dot keys. Okay, my travel time, I didn't have to change. It doesn't feel like I had to change too much. This would be nodes.keys. Nodes. Dot flow rate. Nodes dot. Nodes of node dot edges. Okay. Think we're good still. So now this is node of room dot flow rate. Okay. So now I can do this interesting thing where I have like this bit mask where I can ask a question. I'm gonna add a new class here to track this thing here. This is gonna be called our valve state. All right, public record valve state int. Well, we have a lot. We can't be doing it. I'll do it a long bit mask. All right, so we have a valve state here, and the idea is given a public valve state, turn on a node and a location. We can return. We're going to take our bit mask and or in L.id bit shifted. No. Number one bit shifted by our ID. It's saying I haven't assigned this, so this would be new return new valve state. Bitwise or operator. This should be a long. There we go. All right, so this will only support 64 different locations. So this bit mask, luckily, if we look at our input, we only have 58 locations. Okay, so we have a valve state we can turn on. We don't care about turning off, but we also want a bool is on location L. And to do this, we want to extract out the bit mask. So we need to do a bit mask and ID like that, and we return if this is greater than 0. So we're gonna do an AND, so we take that number, we check, hey, is this thing on? If it is, our number will be greater than 0. Okay, so now this becomes our valve state S, and we can ask is, state or valves state dot is on. So if that room is on, it needs to take in. We can pull out that nodes of room. Okay, so if it is on, this will have 0 effect. Otherwise, it'll have all this effect. And so now we can memoize this thing. Because we don't. I mean, I don't know if that we have to memoize it. We gotta we have to do a thing where for all possible valve states, right? So now, okay. So we have like this benefit thing now. We start at AA. We can sort of like go. Let's see here. Do we care about where we end? I don't think we care about where we end. Where's my problem? You're eventually going to open a mall. Valve C, open valve C. And then they're all open here. And you just let it run. So now I need to construct like the state saying, okay, so at each point, my explorer wants to find the benefit at time t. What's what moving to what room would give the greatest benefit? Right, so and then that's gonna be a bunch of different valve states. Right. And then we want to calculate the best one. Okay. So I have my explorer. And our valve, all right, so public void explore. And our exploration is going to be based on string position. So we're going to have an int time, a string position, and a valve state. And we want to say, all right, if this is going to return the total pressure that we have released. Oh, this is interesting. So it's not quite the benefit. It is the benefit of going there and turning it on, but so the idea is how much pressure is released at this explore step. So given our current position, we sort of can evaluate how much time. So the idea is I visit another location. So string cave.node. Oh, I really only care about my current position. Edges. So from this node, where can I? No, that's not true. Because it might be faster to try. Yeah. So actually, this is gonna say for each string nodes destination. Nodes in cave dot nodes dot keys. So we have to check all of our other locations. We're gonna say int travel time equals cave dot nodes. Cave dot travel time to for each node. All right. So we figured out our travel time to each other node. If the time minus travel time is less than 0, we don't go there because we run out of time. If the this should be from position to end. So if we don't have enough time, we don't visit that location. Otherwise, we sort of have to think about the benefit of going there. So this, for each that if the time minus travel time is less than 0, we continue. Otherwise, we say int benefit int benefit. Well, travel time minus travel time, and then it takes 1 to turn the valve off. All right, so real quick, we don't want to visit locations where no pressure. So if cave dot benefit time minus 1, it takes us 1 to get no travel time. So if the travel time's less than, if we can't get there in time, travel time plus 1 to turn the valve off. All right. Benefit time travel. Why can't I do this? Time travel. Why don't I have access to this variable? Hang on. So int benefit is equal to cave dot benefit of cave dot benefit, and then we're gonna take in time remaining. So it's time minus travel time plus 1. Yeah. 2n with our current valve state. All right, so this is our benefit. This is how much we're going to add to our sum. So it's going to be, and then our new valve state, vs equals state dot turn on n. We're going to turn that on. Oh, we have to get that. We actually have to get the node. Cave dot nodes n. If it's already on, we don't care. That's what I was getting at here. So if state dot is on cave dot nodes at n, continue. We don't want to turn, we don't need to go there. We can skip it. Then we check how long does it take us to get there. Then once we know time used, I'm gonna put +1 here. It's gonna just be time used. And in fact, int time remaining would be time minus time used. So if our time remaining would be less than 0 or equal to 0, less than or equal to 0. No, yeah, less than or equal to 0, then it will get no benefit. All right. Time remaining. All right. Otherwise, the benefit's the amount of time remaining, our state, we turn it on. And so our total is going to be our benefit plus well, not quite. This is going to get, we're like constructing a list of all possible results. Int total is going to be equal to explore time remaining n and new state. And we're going to add that to this is our, we need to memorize this. All right. So this is gonna be a public dictionary of time. Oops. Int string valve state to our total. Yeah. Yeah. And then we just ask, hey, what is it when we have 30 in position AA with the initial valve state? There we go. I got it. Dynamic programming, right? So this is going to be results, and I'll start out here like this. Okay, I think we got this. I think we're gonna get this. So we actually say if, so we'll create a thing here called int string valve state E is equal to time position state, and we'll say if result dot contains, why is everything giving me trouble here? If results dot contains key, return results of key. Otherwise, we do this, we find the total, and our total is our benefit plus exploring the next one. So then we would return this. And if we get through all of that, what do I return here? Now I gotta know. We return 0, I think. So if we get here, any action we take would result in no benefit. So we return 0. Now, moment of truth, right? Public int explore int time string start, and our valve state start equals 0 equals our initial new 0. So we haven't turned on any valves. Ooh. Let me look at my input. If at A, can I gain any benefit from A? Okay, so I can safely ignore A. It's like, oh, well, I have this thing. It's like, do I take the time to turn A on initially? The answer is no. Okay. I really hope this works. Otherwise, I'm going to be debugging here for probably ever. And then we just return explore the time. Well, actually, we can just say that our start position is AA, and this is our initial. All right, let's crash. Let's try it with the example. Explore E equals new explore cave. Yeah. And then E dot explore 30 int most pressure console dot write line most pressure what best Pressure was pressure. All right, let's give it a shot. .NET. The given key AA to A was not present in the dictionary. Oh, I gotta build up my travel times first. Got to build my all pair shortest path. I should probably be part of the parse. 1380 was that? That was fast. Nope. Oh boy. I think I have the right idea here. I think I have the right idea. I just gotta figure out. Just gotta figure out what I'm doing wrong. Let's see here. Closed Explorer. Let's think through this. $13.80. So what are my possible? What am I possibly doing wrong here? My benefit could be wrong. Time remaining. I am including, all right, so it's my travel time plus 1. That'd be the time used to visit and turn on. My time remaining. Is this it? No. Pretty sure that should be less than or equal to 0. So my benefit here should be turning this one on. Console.WriteLine. Let's look at the benefit. Benefit of turning on N with time remaining. Is, I gotta put, would be benefit. Zero. Now I kind of need to track what is the path that I took, which is a little bit harder to do, but I can do add another string here. This is going to be the previous action. Oh, maybe no, because the way I'm adding them in here, previous action here. All right, so string question mark. All right, so we came from this string prev. And then here, our previous node happens to be position. All right. Is that what I really want? Is this still gonna do the same? Let me make sure that didn't break. All right, and I no longer want to return an int. I want to so int is like my total benefit. Oh, hang on. I shouldn't be doing this. Here we go. Result. I'm dumb. Result at my key is equal to the benefit plus exploring all of them. And at the end, I need to calculate which key has the highest value. So these are like all the possible explorations. And then I set that and then I return. And then I return it. I have to, yeah. I was never updating. So this explores. We don't want to return here. What am I doing wrong here? Hang on. I need to I'm doing something wrong. I need to take the maximum of doing this. At each location. So this is going to be a list of int outcomes. Oh, okay. So I need to do this list event outcomes, and then for each one of these I add that in. Then I find the maximum. Outcomes.max. And I set result of my key equal to my maximum. And then I return that. Okay. This should run a lot faster. What was happening is it was doing a depth first search along one path. So one possible outcome was 1380. All right, so this will actually take much longer to run. So I need to, the state should be like 50. Sequence contains no elements. Oh, okay. And if there are no outcomes, it's 0. All right. We'll put 0 as the default in that list. 1651. There we go. Much better. Okay. Whew. I was doing one path and returning it. All right, let's try it. Input. It's gonna be a bigger search space, so give it a. Oh man. Am I not memoizing properly? Let this keep running for a minute. I could really turn this in. I could make it faster by using a bunch of arrays instead. Well, I'm gonna give it a little bit of time. While this is running, I'm gonna go get another little boost, a shot of coffee here, and see if we can see if this returns. If not, sad. All right, I'll be back. I'm gonna see if this finishes. All right, we're back. I think I know what's killing this. It's this this thing here. I don't care. It's making it so that my previous yeah, it's making it slow because now it needs to take into account where it was coming from, whereas before it was only caring about the state of it. This was to allow me to figure out how it's backtracking. Okay, let's make sure this still works on our example. My keys were now getting off because I really only care about this. All right. I hope my brain made proper sense of that. Or not. Oh, come on. Am I getting to the bottoms? My possibles should be... How many valve states do I have? I don't even have that many. have a lot of combinations of valve states. All right. And then time remaining. All right, we're gonna try this. Time, starting position, valve state. And I guess valve state to string would be kind of hard to do. Our valve state is literally just a long, right? Yeah. Right line. Let me make sure I'm getting down here. Time. Time. Key. Plus state. Make sure I'm not recalculating time key state. Yeah, shit. I'm getting cache hits. Why am I printing out? Oh, this shouldn't be key. This should be position. My combinatorics are wrong. My number of combinations is incorrect. So I'm not getting the cache hits I want. I should be getting more cache hits right away, I think. Oh, because I was thinking I only have 50,000... 57,000 combinations. Public int. Yeah, I've got way more than that now. Entry results.count. Yeah, something is this approach must have not been correct because we have way more than 50,000 entries. What did I go wrong? Or is my bit mask wrong? Because I have okay, let me think about this. Oh, I'm gonna leave this running. I'm gonna start a different instance. We're just not getting enough cache. I'm gonna leave this running. I think this will eventually finish, but will take way too long. There's gotta be a more efficient solution. What's going on here? What was that? Hotkey control tilde. There we go. We'll leave that running. The number of combinations is just far larger than I thought. Because there's... Alright, we're close. We're getting close. Leave this running. Alright, so I have all pairs, shortest path. How can I reduce my search space? All of my valves start off. And I do gotta go here in about 10 minutes. So I'm not gonna solve this one live this morning. I really thought I'd be able to time remaining position valve. Let me think about this differently. I should be able to that 17 is actually 17 squared, because those are the number of valves. I think that's the number of combinations at like every step. I need a way to better and analyze the benefit. I'm wondering, can I just... All right. Keep this running, but I think I can actually just find the one that benefits me the most. It's not quite right though, because the amount of time to get there, the like combination of benefits from another position could be better, I think. It's just the benefit at this time. Yeah, my search graph is far bigger than I thought. I'm pretty sure that won't work, because I would say... So if I'm at a position... No, it should work. I should be able to pick a node, go to that node and say, this node has the most benefit at this moment in time. All right, so let's try that. List benefits rather than so I need to find the one that has the best benefit. So it'd be int. I want to find the max benefit. All right, so int benefit equals 0, max b, string n equals position. So if we end up not moving, we just stay in one spot. Int time used. If we just stay in one spot, that's one time. One time used, or time remaining, t time underscore, because I can't think of a better variable. Next position next time equals time minus 1. We just sit here, time minus 1. Max b is 0. We ignore locations where we're already on. We ignore locations where we run out of time. Yeah, this is never gonna finish. Otherwise, we get the benefit and we say if this benefit is greater than my maximum benefit, max b equals benefit. Next position equals n. Next time equals time remaining. I don't think this is quite built. And next, yeah, valve state next state equals state next state equals this. All right. So the result here becomes max b plus explore next time next position next state. All right, let's try that on our example. My gut tells me that this is not right. Solution. Oh, I can't run it at the same time because of this. All right, we'll kill that. Stack Overflow. Okay. What did I do? Next time. If we need the base case of if it's at 0. So if am I missing the part where I'm taking, am I not properly, if time is less than or equal to 0, we can't do anything. So we return 0. So it's sort of saying like, what's the most benefit I could get at this time? All right, let's try that. No, this is not correct. Because it's not correct to just finding the best benefit. The neighbor that has the best benefit isn't gonna actually solve anything. It's like the combination of going to that neighbor plus exploring. This is why this first one worked, but my space is just too big. Probably gonna have to draw this one out. This one's tricky. And I'm almost out of time here for this morning anyway. Let's keep thinking just for a minute. Given this amount of time and this location and this valve state, give us back the total pressure, the maximum pressure we can release. I think the issue is that my valve state is like 17 squared. Or no, it's 2 to the 17. That's too much. That's what's happening. I need a way to, so I think I determined that I actually had 15 nodes. So I'd have, my search space is 11 million. So it will finish. It will finish. If I go back to my previous version and leave it running. But there has to be a better solution. Let me just put it back. Oh, darn. Let us... I just miscalculated my search space is what I would have taken a different approach. I thought my search space was reasonable here at like 58,000, but my search space is actually like this big. So it's the possible time. So I have 30. It's actually 30. How many ticks I need times the number of locations. Although that number is smaller than you might think, because I'm never gonna visit locations that have a size 0. So this is like 15. But the bulk of this size is coming from this number here. So 14 million. Yeah, my search space is 14 million. Let's about 14 million. Let's see. Every time we add something to it, let's report how fast we're going so that we can sort of see results dot size dot count mod. Every time we add in 100,000 things, we'll do a little tick here. We'll do results dot count entries at, and then what is our system's current time? So we'll do a little thing up here that's like public static. I need like a current time millis. Current time millis C#. What is it? Total milliseconds. We'll just write this stupid thing. And environment.tick count. Okay, that's what I care about. Public. So yeah, public environment.tick count. Environment.tick count. What is the return type of this? An int. Oh, it's not even. So private static int. Private int start time. Started at 0. start time is equal to tick count. And then we can actually just call this last tick. Last tick. So now we have our current tick. So every 100,000 we can report how long it took and how many ticks. Gets the number of milliseconds since the system started. All right, so then int current ticks equals environment dot tick count, and we will do int total total ticks is equal to, I feel like there's whole subtrees I can cut off is the thing, and I'm not sure how to do that just yet. I need to be able to prune my search a little bit more. I'm gonna get this started. I'm gonna probably finish it later, but this is just for fun. It's for me to see how slow this solution is gonna be. Last tick, current ticks minus last tick. You can give me the number of milliseconds. At, and then we'll get our total ticks. And there's not even enough ticks in the base problem for this to happen. The default problem's small enough. Yeah. All right. So we'll do 100,000s. Because getting to 20,000 was not that long. All right. And let's try our input. All right. So my and if I'm off by 1 here, my estimate is that it'll be around 30 million, somewhere between 15 and 30 million. And if that's not the case, if we get up too high, then I know that I'm wrong again. But the number of combinations I have is, I think, 2 to the 6, the 2 to the number of entries, 2 to the number of valves that are worth turning on. So like valves that have a state of 0. I'm skipping, right? Let me double check. Is that true? I just did something. If it's already on, no, here. Oh, here's an optimization. If benefit is 0, continue. There we go. All right, this is where okay, so now I skip all of the, yeah, I was testing valves that do nothing. Yeah, I was testing valves that do nothing. So if my benefit is 0, and I was skipping ones that were already on, but I was testing ones that had a benefit of 0, so ones that do nothing. Let's test on our example one more time. Still get that answer. All right. So we should still, oh. Wait. Was that it? Did I just actually solve? Oh, man. All right. Oh, I did it. Okay. I just wasn't... So I was right. I can prune my tree. So maybe my original thought was correct that there's not that many. Maybe it really is 58,000 because I don't have to worry about valves that are turned on or off. Okay. All right, let's read the second part real quick. I should really be going. I've gone overtime here just a little bit. Whew. You're worried that even with an optimal approach, the pressure released won't be enough. What if you got one of the elephants to help you? It would take you 4 minutes to teach an elephant how to open the right valve in the right order, leaving you with only 26 minutes to actually execute your plan. Would having two of you working together be better, even if it means having less time? Assume that you teach the elephant before opening any valves yourself. Giving you both the same full 26 minutes. In the example above, you could teach the elephant to help you as follows. So teach an elephant. You can teach an elephant to fish. What? Wait, what's that? All right. With the elephant helping after 26 minutes, the best you could do would release a total of 1707. What is with an elephant working with you? Okay. Just one elephant, so it's not that I can keep teaching multiple elephants. So my problem... It's like this... I think it's the same problem. Except... I can... As long as the elephant and I don't go to the same room. So it's sort of like the elephant of if I explore this new state. All right, let me save this as part 1. Let me make a commit. Beat complete day 16 part 1. Okay, so all pair shortest path worked. I was able to trim my search space significantly. I think so I'm under 100,000. So I think I was right the first time, where it's actually times this amount. Okay. Because there are... I think it's still to the 2 or something. Anyway, my search space... I'm doing my numbers wrong here. I think this is my search space. I really got to go in 15 minutes. I know I keep changing my mind. I was supposed to go 15 minutes ago, but let's keep going. Let's keep going, because I think I might be able to solve this. If an elephant is helping me, it's sort of the sum. Let's create a subclass of explorer. Oh, it's only at the very first. Okay, it's only at the very first. This is interesting because I need one elephant, and then each of us needs to decide which rooms to go to simultaneously. I think the amount of benefit, this dictionary doesn't have to change, it's just how we explore. So it'd be time. Our time is going to be 26 now, but it's sort of like the sum. Let me duplicate this. Explorer with elephant. So we have an elephant explorer with elephant. We have an elephant with us. We both start at room AA. Okay. From this room, if we've, we're going to do the same thing where we calculate the result. One of us, we shouldn't go to the same room. So it's sort of like we want to do this int my benefit. So this would be I go left with my new state. And then the elephant needs to choose for every possible choice I can make. I need another loop here that's like for each string m in cave.nodes.keys. This would be the path the elephant takes. So I'm going to pick a room, and then the elephant's going to pick a room that's different than the room I picked. Or I guess technically it could choose my room, but my state becomes these things. So I need to do this again. So I'm gonna abstract this out here. I'm gonna do public something, choose room, and the idea is the inside of this whole loop is gonna be here. Yeah, so this needs to return a list of outcomes. Okay, so we'll pull this out here. And we return the max of outcomes. Return the max of our outcomes. So int outcome equals choose room, and we're gonna have to hand it off some stuff. In this case, we need to give it a state. So valve state, a position, and an int time. So like our keys, yeah. So time, position, state. It's gonna give us back a list of outcomes. Let's have it just return an int. So this is gonna choose the best, because this calls explore, it'll end up choosing the best one anyway. So it's like choose room, my outcome. Oh, I need to get this new state back as well. Yeah. Because that's the updated state. So this should be a valve state. This is going to be score or ben score. I'll call it benefit. And next state. So I need to need to track that. I wish I didn't have to go in 10 minutes. I need to know what room I went to that gave me that state. Or what the state is at the end. So I can have this return a valve state. State benefit. All right, so now int benefit valve state. Well, it's not the, I don't want the final state. I just need to know what the valve state is so my elephant knows not to go to that room. So my elephant knows not to go to the room. That's a hilarious thing to say. Okay, so this, hang on. This doesn't return that. This still needs to return that, and it's sort of my benefit, comma, valve state, next. And it's gonna be this as a result of going to this new state. Okay, so now this is gonna be int valve state, and this will be benefit, and it's no longer about finding the max. Yeah, so this is my outcome, valve state, my room, or my my state. So it's just the state of my valves with that room. I guess I could have just returned the room I chose as well. So this starts out with this basic one saying that no state changed. If nothing, no state changed. I have no idea how it's finding the max, but it's definitely not the way I want it to. Because what I need to do is I need to order by this is my R goes to, this choice goes to choice.ben. I should call this benefit. It's gonna be descending or ascending, so it's gonna be the worst to the best. So I really want it to be, can I do a selector here? My compare is A, B, int A, int B goes to B minus A, and I just sort it in descending order. And it can't be removed because it's not a delegate type. What is the compare? Order by. I know how to do it by sort. I'll just sort it. This is my pair. P0 var P1, and this is gonna go to P1.benefit minus P0.benefit. So this will get us in This will get us in our... This will sort it so that the biggest one is first. So it should be outcomes of 0. Okay. So this is going to be my outcome. And then based on the outcome I chose, my elephant should choose an outcome. Int elephant. So I'll do my benefit. Elephant benefit valve state. Elephant state equals choose room. Have the same amount of time, same position, but they should do it based on the room I went to. And then the outcome. This is the total benefit here. That's the max of these two, I think. This is like the actual benefit, or it's either the max of those two or my elephant's benefit. So math.max, my benefit. I think it's always going to be my elephant's benefit. My elephant will always have a greater than or equal to our own. Woo! All right. And this means that we have 26. We teach an elephant to fish. Let's see what it says for the example. Let's see if my program blows up. Ooh. Well, that isn't right. 5 minutes. 5 minutes. 1707 is what we should be getting. I just want to make sure the elephant doesn't go to the same room I went to. Oh. I'm not using an elephant explorer. Explorer with elephant. Try again. Was 0. That's not right. Let's think what happened here. Our sort might be wrong. Because then it would always return 0. Real quick, let's try that. No. We're not adding this. Outcomes.add. Results. Still not right. What is my elephant? Come on, elephant. What are you doing? My benefit, my elephant's benefit. Real quick, just a sanity check. My result should be the same if I were to get rid of this and do my benefit. This should get me... Okay, so that means I've done something wrong here. With this. Oh, but that would mean my time would have to be 30. My time was 30. Okay, so something isn't quite right here still. My explore with elephant with time 30. Let's think. Why does this not give me... Oh, I'm looking at the wrong answer. 1651 is the right answer. Okay. So my sanity check there that my choose room is selecting the best room still. Question is, why? Excuse me. The next state is the new state. And then my elephant state I should be able to just safely ignore my elephant state. But I should have only 26 time left. I'm not correctly adding them together, maybe? I think that's what's happening. It's like the benefits... I'm not calculating the benefit as I go down correctly. Because it's like my elephant, I move. What is... it's still getting just my own benefit. I need, like, what's the benefit of me doing it and my elephant doing it? And it's... We need, like, the sum of our benefit. But it's the total benefit, but I want the benefit at... I really only care about the benefit at that step. Because it's not just my benefit, it's the benefit. All right, so it's my benefit plus the benefit. What is my elephant? All right, is it the sum of these? Console. Yeah, let's not right line. Mine. My benefit. Elephant. Elephant. Benefit. There's like an added something not quite right about how I'm finding the benefits. I'm ending up with just like my benefit. My elephants, is it my, so I think it's going to be my benefit minus my elephant's benefit. So it's like the benefit of the thing my elephant did, and then it's the sum of those two things. Plus my benefit minus my elephant. My elephant's benefit. So like my benefit, I need to subtract out. No. That's... I'm close. I'm so close. It's sort of the sum of our works, though, and I can't... I'm not quite able to get there right now. Unfortunately, I do have to go. So I gotta stop here. If you watch this, thanks for watching. I hope you learned something. I hope you enjoyed watching me struggle a bit. I am happy with the solution I got for the first part. My second part, I'm like almost there. I just have to figure out, I might need to make a change Um, yeah, I just need to figure out the result of me doing this is some benefit, and then I need to add in the bonus benefit I get from my elephant doing this something with me. I haven't quite figured that out, but the search is it's going to be essentially the same, I believe. All right. With that, have a beautiful day. Keep on coding, keep on growing, and you're welcome back anytime.